This hearing will now come to order. I want to wish everyone a good morning and welcome them to our hearing on the next generation of fusion energy research. Before we get started, we have Congressman Rush Holt of New Jersey with us in the committee today. If there is no objection, I would ask unanimous consent that he join us on the dais. Hearing no objections, so ordered. Thank you for being here, wherever here. Where is Rush? Oh, there he is. Hey, Rush. Come on up. We will begin today. Rush, thank you for joining us. Your expertise will be much appreciated on this committee, along with that of Dr. Ehlers. Fusion energy has successfully powered the sun and the stars for billions of years, so it's no surprise that humankind has tried to harness this energy here on Earth. However, we all know that a working fusion reactor has been much more difficult to achieve than our atomic age scientists initially expected. Over the years, there were also some overly optimistic or even, in some cases, fraudulent proclamations by folks who skipped the peer review process and went straight to the media, which has further complicated the popular and political assessment of the extent to which the federal government should continue to support this research. That said, however, according to recent reviews by the National Academies and the Department of Energy, there have been significant developments in the fields of advanced computing, engineering, and plasma science over the last 20 years that have led to a far better understanding of how to create and control a fusion system. Within about 3 years, the National Ignition Facility in California is expected to become the first fusion device in the world to produce more energy than it consumes, though only for at most a handful of brief experiments per day. In Cadarache, France, the large international fusion project called ITER is about to begin construction. This experiment is designed to produce 5 times more energy than it consumes for several consecutive hours. I think my children already do that, however. They're 4.5 years old, and I swear they put more energy out than they consume, as well as 10 times more for at least 500 seconds. That's the expectation at any rate. If these new facilities are successful, they will present a dramatic turning point in developing a viable commercial fusion reactor. Big questions still remain, however, such as how affordable fusion can be in comparison to other options that are known already to produce greater amounts of energy, what the appropriate choices are for materials in a device which contains gases that can be hotter than the sun. But the U.S. fusion program needs to do all it can to ensure these successes and be ready to take advantage of them if and when they occur. I look forward to learning more from this excellent panel of witnesses on how this program should evolve in light of recent developments. We're waiting for Mr. Inglis, but how would you like to proceed, Vern? You want to make an opening comment, or?
Thank you, Mr. Chairman. I'm just sitting in briefly for the ranking Republican of this committee, who will make a grand entrance shortly, I'm sure. But I really appreciate, Mr. Chairman, you holding this hearing. This is an issue that is really dominated long-range energy thinking for many years, but has had very little public successes to back up the standing that they had hoped to achieve. And I sincerely hope that we can learn a lot more about fusion energy, not only in this hearing, but in the next 5 years, and really be able to put it in its rightful place in the hierarchy of energy alternatives that we should be pursuing. It's clear to us that we have to take a different approach in our society in terms of the generation and use of energy. We know much of what we have to do to change our use of it. We even know a great deal about what we have to do to develop alternative methods of producing usable energy. But we certainly don't know as much as we need to know about fusion energy and what role it can and should play in the future. So I thank you for holding this hearing, and I will yield back.
Thank you, Dr. Ehlers. If other members wish to submit additional opening statements, those statements will be added to the record. And, of course, when Mr. Inglis arrives, we will accept his statement as well. At this point, it's my pleasure to introduce our extraordinarily distinguished panel of expert witnesses. Dr. Edmund Synakowski is the Director of the Office of Fusion Energy Science at the U.S. Department of Energy. Dr. Riccardo Betti is the Assistant Director of Academic Affairs for the Laboratory for Laser Energetics at the University of Rochester. Dr. Raymond Fonck is Professor of Engineering Physics at the University of Wisconsin. And I'll yield to our distinguished chairman, and then following that, well, I was our distinguished chairman. I'll yield to Bart, I didn't see you were here. Mr. Gordon, sorry, distinguished Chairman Mr. Gordon, I didn't see it. Mr. Gordon is here, of course, to introduce Dr. Thom Mason, Director of Oak Ridge National Lab.
Thank you, Dr. Baird, and again, as I've said before, you've been the workhorse. This has been the workhorse subcommittee for our full committee, and I thank you for another very excellent hearing with an outstanding group of witnesses. Thank you all for coming. And I'm pleased to have the opportunity to welcome to the subcommittee today an adopted Tennessean and the director of the Oak Ridge National Lab, Dr. Thom Mason. Dr. Mason earned his Ph.D. in experimental condensed matter physics, something that Mr. Davis and I talk a lot about. After touring the world, he came to Oak Ridge in 1998, and then in 2001, he was named director of the lab's Spallation Neutron Source Project, an impressive $1.4 billion project that was finished on time and under budget. And Oak Ridge now, then later in 2007, he became director of the lab. And Oak Ridge, he's going to describe today his critical role in managing the U.S. contribution to the ITER reactor. They are in East Tennessee. I'm in Middle Tennessee, but Mr. Davis represents many of the folks that work there, so I will yield to Mr. Davis to pander for a few minutes.
I'm glad you said a few moments or a few minutes. It takes me a long time to get words out. I speak a little bit slower than perhaps some folks. Mr. Chairman, thank you for the work that you do on this committee, and we in Tennessee are certainly lucky and very proud of the accomplishments that you have. And Bart and I represent an area that has in it the Cumberland Mountains, and our folks there say they're proud to have two congressmen. I think they're prouder of Bart, probably, Gordon, than they are of me, since he's chairman of this committee. I'd like to add to what comments you just made, and I'd like to add that Oak Ridge is a pillar of the community in Tennessee, supporting world-leading research initiatives in energy, environment, national security, and computing, as well as providing good jobs and performing educational outreach to our students. We're lucky to have this critical scientific resource in our region and such an accomplished and dedicated scientist and leader as you are. Dr. Mason, I'm very happy that you're here today to provide valuable insights on the future of fusion research both at Oak Ridge and abroad. I look forward to your continued strong leadership at this laboratory in Oak Ridge. It has been great working with you, and as I travel to Oak Ridge, to the lab, or whether it's at the Spallation Neutron Source or eventually go to where NNSA is there at Y12, I realize that this area of the world, this area of America, and this part of Tennessee has been a valuable asset in scientific research and will continue under your leadership. Thank you for being here.
I thank our Oak Ridge boys for their introduction. I apologize to the chairman. I hadn't seen you here, Mr. Chairman, so I was puzzled by what appeared to be a strange third-person self-reference here. I would now be happy to recognize our guest at the committee, Representative Rush Holt, to introduce our last witness, and Mr. Holt will be followed by Dr. Ehlers, who wishes to offer comments as well.
I thank the chair, and I'm pleased to be with you and my distinguished colleagues today, and also with the distinguished panel. In fact, I've been asked to introduce Dr. Prager, but I could equally well spend time introducing and praising Dr. Synakowski, Dr. Fonck, all three of whom have been constituents in the 12th Congressional District in New Jersey, but more importantly, all three of whom have been leaders, world leaders, in advancing plasma physics and fusion sciences. They all have contributed to what we now see, the promise of fusion with essentially unlimited globally available ingredients, with great environmental attractiveness, with no harmful emissions or high-level radioactive waste or connection to proliferations of weapons materials. In other words, a technology well worth undertaking. They will be well prepared to address today how realistic and practical this may be. I would say at least possibly, and I would go so far as to say probably. The progress has been great by any measure, exceeding predictions. Certainly if you look at achievements per dollar spent, in power contained, millions of watts, in plasma sustained, improvements by factors of hundreds of thousands to what amounts to an eternity in plasma lifetimes. development of an entire new field of science, plasma physics, with theoretical and practical contributions not just to materials and engineering and science, but to daily lives. The progress, the promise, the justification of spending taxpayer dollars, significant taxpayer dollars, have been recognized by domestic and international advisory committees, in some cases on which our panelists have served or which they have chaired, and also recognized by the actions of many other countries. It's worth noting, as we talk about the fusion energy program in the United States, that the United States was once, for decades, the world leader. We could be again. We should be again for all the reasons. If we are, it will be in part because of the work of some of these panelists. Dr. Prager has worked at a number of the places where this significant work has been done. General Atomics in San Diego, Columbia University in New York, University of Wisconsin for many years, and he's chaired the Fusion Energy Advisory Committee. He's chaired the Division of Plasma Physics of the American Physical Society. You'll notice I spoke earlier of creating an entirely new field of science growing out of the work of Lyman Spitzer at Princeton 40, 50 years ago now. He served, Dr. Prager also served as president of the University Fusion Association, so he represented the large academic contributions of this field as well. Recipient of the Dawson Prize and the Leadership Award of Fusion Power Associates. So I'm pleased to introduce Dr. Prager to you, but also commend to you all of the panelists whom I know personally and cannot praise highly enough. Thank you.
Thank you, Dr. Holt. Dr. Ehlers.
Thank you, Mr. Chairman. Just a brief comment in view of the comments of the two gentlemen from Tennessee sitting on the dais here, and especially to our chairman, Mr. Gordon. When they were making their comments about Oak Ridge, it suddenly occurred to me it's been at least 30 years since I've been to Oak Ridge. It's been probably 20 since I've been to Argonne and 10 since I've been to Fermilab. Members of the committee, these are the crown jewels of our research effort. And I think members of the committee should be visiting these laboratories more often. So my plea to Chairman Gordon is perhaps we can start organizing CODELs where members of the committee can go visit the national labs on a rotating basis. I think it would be extremely beneficial for the members of the committee. Yield back.
I hear there are visa problems for some of us to get into Oak Ridge, but we've been joined by the ranking member, Mr. Inglis, and we'll recognize him. First of all, welcome him. I know he had a panel he was attending prior to this, so I appreciate his presence. And well, thank you, Dr. Ehlers, for so ably filling the role in the absence. And Mr. Inglis, welcome. Thanks.
Thank you, Mr. Chairman. Good to be here.
You've introduced everybody. You can offer opening remarks.
Well, I think that Dr. Ehlers filled in very well. Thank you, Dr. Ehlers, for filling in. And so I'm looking forward to hearing the testimony because it's very important and very exciting. The key question is how to make it work. So looking forward to learning more from that from you. So thank you, Mr. Chairman, for holding the hearing.
One of the things I greatly respect about Mr. Inglis is he recognizes when everybody said everything and he doesn't have to say it again. So that's a rare quality in Congress. And with that, we will proceed to our experts, and we'll begin with Dr. Synakowski. Thank you very much.
Thank you, Mr. Chairman, Ranking Member Inglis, and members of the committee. I've been director of the Federal Fusion Energy Sciences Program since June 7th of this year. And I'm thrilled to join this office when the scientific readiness, opportunity, and urgency in fusion are extraordinarily resonant. The pursuit of fusion energy embraces the challenge of bringing the power of a star to Earth. Fusion's promise is enormous: nearly limitless fuel supplies, large-scale energy production, no greenhouse gas emissions. We are entering a new age in fusion science during which our knowledge base will be put to the test as researchers will undertake a fundamental set of new studies of fusion energy's viability. At the heart of fusion energy in the stars and on Earth is the world's most famous equation, E = mc², which describes the fundamental relationship between mass and energy. The challenge is getting atomic nuclei of the fuel to bind together to form heavier elements, releasing enormous quantities of energy in the process. In the lab, we use hydrogen isotopes as the fuel, and I've had the privilege of being part of experiments that have generated millions of watts of fusion power. The science underpinning much of fusion energy research is plasma physics. Plasmas are hot gases, the stuff of stars, and over 99% of the visible universe, lightning, flames. Plasmas are routinely confined by magnetic fields and heated in laboratories to fusion conditions. The tokamak, a Russian invention from the 1960s, is studied worldwide and is the leading candidate magnetic bottle for creating fusion energy. Dramatic progress prompted the National Academy of Sciences in 2004 to urge the U.S. to take a landmark step. It should participate in a fusion experiment in which the plasma burns, or generates more energy than is used to heat it externally, and in large part heats itself. In response, the U.S. agreed to participate in the ITER project, to be built in Cadarache, France. We view ITER as a scientific instrument with the flexibility to reveal critical requirements for fusion's optimization. The 7 members of ITER are China, the European Union, India, Japan, Russia, South Korea, and the U.S. Construction will take place over the next decade, with burning plasma experiments slated to take place in the 2020s. The U.S. is committed to bringing a strong and effective approach to project management in ITER's design and construction. Another approach to fusion is to compress the fuel extremely rapidly and to rely on its inertia to confine it long enough for fusion to occur. This is being studied by the National Nuclear Security Administration for stockpile stewardship applications, and a joint program to study this extraordinary state of matter is being forged between NNSA and my office that will engage a broad array of laboratories and universities. Tests of this approach are being planned for the National Ignition Facility. If successful, they will be historic. The National Academy of Sciences has emphasized the importance of studying this plasma state to both energy research and to a rich array of scientific questions. ITER's success, its chances of success, and our prospects for deep scientific return are intimately interleaved with a broad domestic research program in the fusion-related sciences. In the U.S., our multi-institutional program in experiment, theory, and computation is rich in discovery and impact. It is globally respected for its depth, accomplishment, and scientific aesthetic, and has had a major impact in the ITER design and research plan. Research is supported in 38 states at national labs, private industry, and about 60 universities. U.S. researchers participate in about 75 joint international activities, and about 340 graduate students partake in fusion energy and general plasma science research. Strategic planning is underway aimed at filling gaps in the world so as to assert U.S. leadership where it best advances fusion as a whole while maximizing U.S. scientific return. For magnetic fusion, the scientific challenges can be broadly stated as follows. First, understanding and optimizing the burning plasma state. Experiments, theory, and simulation have significantly advanced our understanding of what to expect from a burning plasma and will continue to do so, but ITER provides the only platform planned to directly test and expand our understanding of this complex physics. Second, understanding the requirements for extending the burning plasma state to long times, days, weeks, and longer. Many aspects of this are pursued in the U.S., and the second 10 years of ITER's operation will put our understanding to crucial tests. However, overseas fusion programs are set to assert leadership, in part through new billion-dollar-class research facilities in Europe, Japan, South Korea, and China. We are exploring growing our collaborations to increase their impact and the knowledge returned. And finally, third, advancing the material science for enduring the harsh fusion plasma environment, for extracting energy, and for generating fusion fuel in situ. We will be exploring what is required to develop a materials and fusion nuclear science program, one that addresses the necessary fundamental scientific issues while weaving the results and advances into our best concepts of future fusion systems. Thank you, Mr. Chairman, for providing this opportunity to discuss the Fusion Energy Sciences program. And this concludes my testimony, and I'd be pleased to answer any questions you may have.
Dr. Prager, you're recognized.
Well, thank you very much, members of the committee, for this opportunity to discuss fusion energy.
Where are they?
And thank you, Congressman Holt, for the kind opening words and for your deep engagement and expertise in this topic. As he said, I'm director of the Princeton Plasma Physics Laboratory, which is a DOE national lab managed by Princeton University dedicated to developing fusion energy. There are two complementary approaches to fusion. In one, as you've heard, powerful lasers compress a tiny pellet of fuel, releasing fusion energy in a flash. the National Ignition Facility will tremendously advance the physics for this approach. I'm here to discuss the approach known as magnetic fusion, in which the large hot plasma is confined continuously by powerful magnetic fields. As I hear you already well recognize, fusion energy is one of the most challenging physics and engineering quests ever undertaken. It will be key to solving perhaps the most pressing problem confronting the world today, the absence of sustainable energy. By any metric, we're far along the road to commercial fusion power. In the past 30 years, we've progressed from producing 1 watt of fusion power for 1,000th of a second to 15 million watts for seconds, and ITER will produce 500 million watts for 10 minutes and longer. Driving this progress has been the development of an entire new field of science called plasma physics. Outside reviews continuously laud the progress of fusion. The most recent National Academy study notes remarkable progress in recent years. But my focus today is the future, the remainder of the journey to fusion power. My comments are informed by the just completed study by the U.S. fusion community commissioned by DOE, known as the Renew Report. 200 fusion scientists undertook this one-year study that identifies the remaining scientific issues to resolve for fusion power. A fusion system consists of the hot plasma core and the surrounding material structure. We are ready to move forward on the 2 major challenges to better control the plasma and to develop new materials. The 2 problems are coupled since the plasma and the material structure interact with each other. Our ability to control the 100 million degree plasma core is quite amazing, yet we have more work to do to sustain the plasma indefinitely and controllably. The sophistication of plasma science now offers new opportunities. For example, designs of magnetic configurations are possible now that were nearly impossible even to conceive 20 years ago. They are possible only with modern computers. Building upon the foundation of the mainline tokamak approach, these designs produce plasmas that persist indefinitely and are so well controlled as to reduce the severity of the materials challenge. It is crucial that we establish a research program in materials for fusion. Materials must be developed to withstand the intense heat that emerges from the plasma. But full solution of the materials challenge ultimately requires study of materials in a true fusion environment with the intense flux of neutrons that are produced in the fusion reactions. It is time to lay the groundwork for such a facility, sometimes called the Fusion Nuclear Science Facility, since it exposes materials to a nuclear fusion environment. If this facility were designed somewhat more aggressively, it could possibly demonstrate net electricity production. Design studies are required to identify the wisest next step in these directions. The Princeton Plasma Physics Lab aims to solve a broad range of fusion science challenges. Our core capabilities in plasma physics enable us to attack crucial problems in the fusion plasma and in materials exposed to the intense plasma heat. The major experiment at our lab is laying the physics basis for a fusion nuclear science facility, is advancing fusion science broadly, and is investigating novel material boundaries. We are contributing to the design and fabrication of ITER and are preparing for research in ITER. We hope to play key roles in a fusion nuclear science facility which would not be located at our laboratory. And we are developing plans to realize experimentally at our laboratory the new steady-state approaches to fusion energy that could prove so essential to the feasibility of fusion. When I began my research career, the U.S. was the world leader in fusion, with the best facilities, arguably the most innovative program. Scientists from the world over flocked to our labs. Japan sent research teams to U.S. facilities to learn the trade. An alarming reversal of that flow of scientists is now underway. The U.S. has not built a major new fusion facility in decades. The rest of the world is seizing the opportunities. Major facilities more ambitious than anything in the U.S. are starting operation or are under construction in China, Japan, South Korea, Germany, and France. Our effort has dwindled to a fraction of that of Europe and Japan. The time is ripe for the U.S. to reverse its slide. Opportunities, such as we are discussing today, abound to restore the U.S. to world leadership and move us aggressively toward carbon-free, abundant fusion energy. And I'll just close by inviting all members to please visit our laboratory, which is a short train ride up the coast. And with that, thank you very much.
Thank you. Dr. Mason.
Mr. Chairman, Ranking Member Inglis, and members of the committee, thank you for the opportunity to appear before you today. My name is Thom Mason. I'm the director of the Department of Energy's Oak Ridge National Laboratory, and unlike the other members of the panel, I'm not an expert in fusion. But as director of DOE's largest multi-purpose laboratory, I oversee a broad program of energy-related R&D that includes magnetic fusion, and it's from that perspective that I see fusion research as an essential part of the nation's energy R&D portfolio. You've heard how this is a promising source of energy that uses widely available fuel and produces no greenhouse gases or long-lived radioactive waste. In fact, one could say that the fuel for fusion is smart people and high-end manufacturing. And so from that point of view, from the point of view of U.S. competitiveness and the type of energy source that is worth seeking, I think fusion is significant. Its science and technology base is now mature enough to warrant a significant investment in determining our readiness to advance to a prototype fusion reactor. ITER is an international project to demonstrate the scientific and technological feasibility of fusion energy. It is being built at Cadarache in France by 7 partners: the United States, Russia, the European Union, Japan, China, South Korea, and India. Each partner is responsible for a share of the hardware, personnel, and cash contributions towards common expenses. This international partnership presents an extraordinary number of technical and management challenges. ITER will be twice the size of the largest existing fusion experiment. It's a first-of-a-kind experimental facility made up of a large number of complex systems provided by suppliers all over the world, and they must be integrated into a device that can function under extremely demanding challenges. The ITER organization has also faced the challenge of standing up and staffing a new multinational organization to provide coordination, project management, integration, and engineering, while overseeing efforts to finalize the design and supervise construction in Cadarache. Given these challenges, it's not surprising that there have been some teething pains. For example, in the U.S., we've struggled to secure funding for ITER during some very tough budget years. But now, with the strong support provided by Congress in fiscal year 2009, for which we are very grateful, we're on a sound footing. Today, the ITER organization has 2 urgent tasks: completing the overall design and establishing realistic cost and schedule baselines. The U.S. fusion community is fully engaged in the execution of these tasks. Oak Ridge has hosted and led the U.S. ITER Project Office since 2006. We're responsible for all U.S. activities supporting ITER construction. The estimated cost of these activities is between $1.4 and $2.2 billion, so this is a heavy responsibility, and it's one that we take very seriously. The office was located at Oak Ridge to take advantage of project management expertise developed during the Spallation Neutron Source project, which, as you've heard, was a $1.4 billion neutron scattering facility that was designed and built by a partnership of 6 Department of Energy national laboratories. It was completed on scope, on schedule, and on budget in 2006. We're working with other national laboratories, industry, and universities to deliver the U.S. contributions to ITER. Recently, 2 contracts worth $34 million were awarded to U.S. companies, one in Waterbury, Connecticut, and one in Carteret, New Jersey. The New Jersey supplier has also received a contract from the European Union's ITER domestic agency. This speaks well of the ability of U.S. companies to compete internationally for work supporting ITER. More than 160 companies and universities in 33 states have worked directly on the project, and many others are interested in future procurements. The U.S. ITER team also provides substantial support to the international organization, developing systems engineering procedures, technical baseline documents, project management plans, and so forth. As ITER proceeds through construction into operation, Oak Ridge will continue to play a substantial role in fusion, and the U.S. ITER project will remain a high priority. We will use our distinctive capabilities in materials R&D, nuclear technology, and high-performance computing to advance fusion science, technology, and engineering. One specific focus will be next-generation fusion nuclear science facility to answer questions that lie outside of ITER's scope. Our strengths at Oak Ridge position us to lead the technical and programmatic planning for this facility, and we will work with the U.S. community to bring it into being at an appropriate pace. ITER represents an opportunity for the DOE national laboratories, U.S. universities, and U.S. industry. We're now positioned to make substantial contributions to ITER and to reap the rewards it will provide in terms of increased scientific knowledge, high-tech jobs that will help us rebuild U.S. manufacturing capacity, and training for fusion scientists and engineers who work on ITER to bring home what they learn. A sustained investment in ITER is essential to realizing the benefits of this extraordinary effort. We also need a vibrant domestic fusion program to take advantage of the knowledge gained from ITER and to continue advancing toward commercial fusion power. It's a major step forward. ITER is a major step forward, but will not answer all of our questions. Congresswoman Zoe Lofgren has introduced a bill calling for a comprehensive plan to identify the R&D facilities needed to ensure the realization of practical fusion energy, and this is a vital step in setting the direction of the U.S. fusion program. The bill also calls for investing in U.S. capability in fusion engineering science that will enable us to develop the materials and enabling technology needed to realize the full benefit of ITER to take the next steps toward fusion demonstration facility. Sustained support for fusion engineering science and facilities is essential to successful development of this future energy source. As we search for sustainable energy solutions, we need a balanced R&D portfolio that includes both near to mid-term improvements in energy efficiency, renewables, and fission, along with electrification of our transportation sector, and fusion as a source of clean, safe, and abundant base load power is in the long-term interest. Thank you again for the opportunity to testify. I welcome your questions on this important topic.
Dr. Betti.
Mr. Chairman, Ranking Member Inglis, and members of the committee, I'm Riccardo Betti, professor at the University of Rochester. Thank you for inviting me to testify today about the status of inertial fusion energy research and a vision for the future. Inertial fusion uses the same thermonuclear reactions and the same hydrogen fuel as magnetic fusion. Like gasoline in the cylinder of a car engine, fusion fuel must be ignited in order to produce useful energy. An ignited fuel can produce fusion energy that can greatly exceed the input energy. If the energy output is greater than the input, then we have an energy gain, and only then fusion becomes an energy source. Thermonuclear ignition has been a scientific quest since the 1950s. Like at no other time in history, we are now close to demonstrating ignition and energy gains in the laboratory. The path toward economically viable inertial fusion energy involves three crucial elements. First, the demonstration of ignition. Second, the demonstration of high energy gains. And third, the development of the technology for a power plant. In the near future, the National Ignition Facility, the NIF, at Lawrence Livermore National Laboratory, by far the world's largest laser, is expected to achieve the first demonstration of thermonuclear ignition in the laboratory by compressing a tiny pellet of solid cryogenic hydrogen fuel using lasers. The current status of inertial fusion energy research in the United States is dominated by the National Ignition Campaign, with the goal of achieving ignition on the NIF. The National Ignition Campaign is funded for reasons of national security by the Stockpile Stewardship Program under the National Nuclear Security Administration, the NNSA. In parallel to its national security mission, the National Ignition Campaign will be able to address many aspects of the physics principles of inertial fusion energy, including ignition and energy gain. The National Ignition Campaign involves many institutions and major NNSA facilities. It is crucial to provide adequate funding to the National Ignition Campaign because achieving thermonuclear ignition in the laboratory is a milestone in the development of science and energy security. This goal should not be undermined by lack of funding. Not now, since we are so close to achieving ignition. The next step after ignition is the demonstration of high energy gain. For a viable power plant, the fusion energy output must greatly exceed the input energy to the fuel by more than 100 times. It is unlikely that the NIF will achieve the high gains required for inertial fusion energy. The current configuration of the NIF will test one approach to inertial fusion, the indirect drive approach. Other inertial fusion concepts like direct drive, fast ignition, and others, funded through the Office of Fusion Energy Sciences, the OFES, and NNSA, have the potential to generate the gains needed for inertial fusion energy. Some of these concepts can be tested on existing NNSA facilities. But unfortunately, the very limited access to these facilities constitutes a serious impediment to progress in this important area and to the achievement of high energy gains for inertial fusion energy. OFES and NNSA have already formed a joint program to support high energy density physics research. This partnership should be strengthened to increase access to NNSA facilities to study high-gain inertial fusion energy concepts. Achieving ignition and high gain does not imply that economically attractive fusion energy is just around the corner. Major technological and engineering challenges will still remain even after ignition. Before starting a major energy development program, it is prudent to undertake an assessment of the different options. This can begin immediately with a small exploratory technology program. A power plant requires a driver to compress the pellet, a target chamber, and many other systems. The driver is the most complex and expensive component of the power plant. Several drivers have been proposed. Lasers are the most developed drivers. Other drivers will likely require longer development paths. An exploratory technology program should be started with the goal of assessing and selecting the most attractive driver in order to move quickly towards an expanded energy development program once the National Ignition Facility has demonstrated ignition and energy gain. Thank you, Mr. Chairman, for allowing me to testify on the next generation of fusion energy research.
Thank you, Dr. Betti. Dr. Fonck.
Mr. Chairman, excuse me, Ranking Member Inglis and members of the committee, thank you for the opportunity to testify today. I got the instruction from your letter to say what our vision for the next 10 to 20 years is, and I thought about it and said, the biggest vision is we should not have this hearing again in 20 years. We should not be talking about fusion energy science. We should be talking at that point about fusion energy development, and there's a crucial difference. So to answer your question, I will give you an example of a path we could take to pursue in the next 10 to 20 years and to get in that direction. Well, in spite of the scientific progress we've made, it's no secret there's skepticism on the credibility or timeline of fusion energy. But much of that can be traced to the fact that the full range of technical challenges has not been addressed. These challenges are, some of them have been mentioned, demonstrating and exploring the burning plasma state, creating predictable high-performance continuous plasmas, taming the plasma material interface, and harnessing fusion power from the very energetic neutrons released in fusion. Addressing these four challenges would provide the knowledge base to establish the credibility of fusion as an energy source and motivate a decision to establish a fusion energy development program. There's been outstanding progress in fusion energy science, it's been mentioned here already, under the auspices of the Department of Energy. Most of this has focused on the properties of the extremely hot fuel, or plasma, required for fusion energy reactions to occur. But it's very important, and it must be emphasized, that fusion science is not just plasma physics. The frontiers of fusion science research are moving to the critical issues of the last two fusion challenges, the plasma wall interactions and harnessing fusion energy. At the same time as these frontiers are moving, our experimental facilities are aging. Our leading experiment is over 20 years old. The next generation state-of-the-art facilities and capabilities are being developed outside the U.S. The fact that we have not positioned ourselves to lead in addressing the first two challenges because of these aging facilities, and we haven't built anything in 20 years, puts us in a unique position, however, of being able to address more aggressively the last two challenges of the fusion challenge. An emphasis on the complex processes occurring in the plasma material interfaces, their integration with the systems that extract energy from the fusion system, and the effects of the fast neutrons on those processes should be the focus of the domestic U.S. program in the ITER era. This program and ITER together will address most of the critical issues underlying the credibility of fusion energy. Just as importantly, it starts the U.S. on the path to benefit economically from its long-term investments in fusion science research. Indeed, the intellectual property rights that accrue from the development of fusion will concentrate in these areas, not in the plasma sciences directly. So it's time to create a plan to put the U.S. fusion program on a trajectory towards leadership in the next generation of fusion research. To accommodate realistic budgets, specific programs and facilities in our program will need to be redirected or completed to free resources for these new directions. Domestically, the program should move to address the pending nuclear and energy-related issues that fusion will present. These scientific challenges will be addressed first in small-scale studies, materials studies, computational modeling, etc. But this effort should culminate in a national integrated fusion nuclear science test facility as the central fusion research facility in the U.S. It will provide the needed integrated test of our understanding of the coupled plasma wall energy conversion systems. Whatever form this facility takes, this centerpiece experiment in the U.S. should be a deuterium-tritium facility to access the full range of fusion nuclear issues. The transition of the domestic program to an increasingly strong focus on fusion nuclear sciences can be executed over the next decade or so, concurrent with the construction and initial operation of ITER. As ITER construction winds down, the roll-off of those funds could be applied to this new national facility to meet the new challenges. Pursuing this program would vault the U.S. program into leadership of critical areas critical areas of the overall fusion challenge. In the ITER era, the research activities on ITER and this U.S. program would arguably define the centers of gravity of fusion science and engineering development and will expedite the decision whether to develop a demonstration fusion reactor, either by the U.S. government or industry or some combination thereof. So there's a pressing need for plans, A, to evolve a world-leading fusion nuclear science program under realistic budgets, and B, to develop the technical case for an evolution of the program into a fusion energy development program as soon as it can. To support developing those plans, the planning of scientific missions and conceptual designs of requisite facilities to match those missions should begin immediately. Support of H.R. 3177, the Fusion Engineering Science and Fusion Energy Planning Act of 2009, would provide funding to start this transformation of the program. Finally, I just want to comment on inertial fusion because I've been concentrating on magnetic. The campaign to demonstrate ignition of fusion plasmas via inertial confinement in the National Ignition Facility is imminent. The achievement of ignition in NIF will be exciting and historic. It will rightly demand a reexamination of our national position on inertial fusion energy, or IFE. As the ideas and proposals for moving forward towards an IFE program evolve after results are obtained from NIF, it would be valuable to have a disinterested expert panel outside the community evaluate the prospects for inertial fusion energy to inform and motivate any decision about moving forward to a new inertial fusion energy science program. Again, thank you for the opportunity to address the community.
I thank all the panelists for not only your testimony today, but for your very distinguished careers and your service to our country and as scientists. And I want to ask a number of questions, and will recognize myself for 5 minutes to do so. I want to put my questions into context. That the context is known, and I often mention it regardless of the topic at this hearing, but it's worth putting forward. The hearing is in the context of a time when our country faces an $11 trillion debt, a $1.4 trillion deficit over the last fiscal year. That's our fiscal situation. Our energy situation is that we, as I believe, the evidence is compelling that we face global overheating and acidification of our oceans. The pace at which we need to make significant cuts in CO2 and other greenhouse gases is much more rapid than any of the proposals currently moving through the Congress, and I think more ambitious than any of the proposals in terms of our reduction of greenhouse gases. That puts a budgetary constraint and a timeline constraint. And so with that as context, let me ask a series of questions so I can understand the sort of time frame we're dealing with. Just first of all, how would we speak of ignition, which I understand is when more energy is put out than put in, for layman's terms. What is the longest period of ignition achieved so far in any of our modalities? In terms of time, how much time?
To date, actually, no plasma has ignited. We have had plasmas with controlled fusion reactions. An analog I like to use is that it's been like burning wet wood. We've created a fire. We've controlled the fire. When we take away the external flame, the fire goes out.
Okay. Let's suppose we achieve ignition. So the challenge, I think, is ignition. Once ignition is achieved, this is not an easy thing, and you folks have dedicated your careers, and brilliant as you are, to this, and many others before you, and I'm sure after. So once if and when we actually achieve ignition, that's a eureka moment in a way, but it's not like all our problems are solved because now we've got more energy coming out. But the challenge is capturing that energy. You've got to somehow capture it. My understanding is that and correct me if I'm wrong, and this is not meant to in any way pejoratively, but basically the way we're going to actually capture that energy is a good old-fashioned way of making water hot and turning turbines. Is that the model we're doing? It's really great that we're still doing steam engines. I just love this. It's I don't mean that critically, but it just kind of blows your mind that we're going to all this trouble to heat water up.
It is a remarkable thing to go from E equals MC squared to boiling water and turbines. But that's essentially the train you're talking about. Right?
But so it's really important for this committee, and I think for Americans and taxpayers to understand that just because we get ignition doesn't mean we can now expect, then next week we're going to turn the lights on with energy produced by fusion energy, right? We've got to somehow then find a way to actually harness that energy, and the current model is again through steam-driven turbines, right? Is that Dr. Betti?
Yes, but there are two aspects. Ignition will prove the physics of fusion. Making energy after ignition requires the development of the technology, and often the development of the technology is faster than the development of the physics. So that is why it's so hard, because we haven't proved the physics yet. And then we count on the technology to move a lot faster and turn this physics success into making electricity.
But there's some real challenges there. Then, I mean, in terms of just
Major challenges.
the material science of what kind of material can contain these reactions and sustain the bombardment of the neutrons, et cetera, right? I mean, so we've got some challenges ahead. Dr. Prager?
Well, I think you're exactly correct, and a lot of the suggestions you've been hearing from the panel members get exactly at the questions you're pointing out need to be resolved. How one harnesses the fusion power is sometimes the expression used. So there are ideas to set up a research program to deal exactly with that question, in addition to the remaining physics questions.
Okay. Then there's the next question. Okay, so let's suppose theoretically we can do it. We solve the physics problem. We demonstrate that ignition is possible. We contain it with the magnetic fields. We heat the water up. Then there's this little nagging problem of cost per kilowatt hour. This seems to be a bit of a challenge at present. We've got any thoughts about cost per kilowatt hour?
I don't want to offer up a number, but I would sort of characterize it a little bit in the sense that with fusion, no one is talking about electricity too cheap to meter. I think everyone has learned the lesson that you shouldn't confuse fuel cost with what things actually cost. Fusion will be a fuel source that's dominated by capital costs because there is no ongoing substantial fuel cost. And of course, capital costs have to do with financing models and lifetimes and things that go well beyond the realm of physics and engineering. But if you look at the scale of plants that are being contemplated and the complexity of them, I would say it's not fundamentally different than the kind of cost model you see associated with fission. What we have seen is that fission power is actually very cost competitive, but because of the large upfront capital costs, it's difficult for risk markets to handle, and that's why things like the loan guarantee programs and so forth are very important. And so I think with the right sort of policy framework, it can be very cost competitive. Understanding that things like the programs that are in place now that are hopefully going to get us going with new starts in fission are likely models that would have to be explored, particularly at the outset when the risk is much higher.
Yeah, which leads to the question, for me, one of the challenges we face is we have this imminent problem of global overheating and ocean acidification. We have this tremendous budget debt and deficit right now. And we have alternative technologies that today you can buy off the shelf that produce net energy output with the existing fusion energy thing called the sun at a known kilowatt per hour generation. That if you invest X, with money being both finite and fungible, if we invest X amount of dollars now, we can lower our carbon output, et cetera. And so I think it's just really important for us to understand that the when of this, so I've been talking costs and how and stuff, the when seems to me to be a good bit down the road. When I mean when we could actually generate significant replacement of existing energy sources. I'd be shocked if any of you'd say any less than 20 years, and I'd guess it's more like 50. I may be wrong.
I alluded to this a bit when I talked about the portfolio of energy choices, and I would kind of divide it into three categories. In the very near term, the most fruitful sorts of investments we can make are in energy efficiency. There's a lot of things that we know how to do that can immediately reduce demand, and the cheapest form of energy is the energy you don't need. In fact, most of the energy efficiency steps, which represent about a third of what you need to achieve the types of CO2 emissions goals that people are talking about, cost you a negative amount of money. In other words, you save money by doing it. And so there's no question in the very near term that is the low-hanging fruit that we need to go after aggressively. Things like renewables, wind and solar we know we can make them work, but they are not yet cost-effective, although there's a lot of promising research directions that will improve that, and scale up will bring down the costs. But they are intermittent. And so certainly when the sun is shining and the wind is blowing, we will want to be harnessing that energy and the environmental benefit that goes with it. But it is not a baseload generating capacity. We do need baseload capacity that we know will be on when people switch on the light switch, and will allow us to buffer the intermittent renewables. And fusion has the possibility to offer a baseload generating capacity that does not have a fuel constraint. Now, right now, most of our baseload capacity comes from coal. And in terms of timeline and risk, I would say our chances of being able to sequester CO2 from coal-fired plants at the scale we need to is not greatly different from the challenge we face in fusion.
I don't dispute that.
And we can't be sure that either one will work.
Yeah, I think that's a good point. My time is up, passed up, but I wanted to establish that line of evidence and questioning. And Mr. Inglis is recognized for 5 minutes.
Thank you, Mr. Chairman. I wonder if others on the panel agree with Dr. Mason's assessment that fusion is in the league of fission in terms of the capital cost and the involvement that we'd have. And is that, do you agree with that, Dr. Prager?
Yes, I would. One of the guiding principles, almost too much so, of the fusion program over the decades has been economic attractiveness. It has guided the kinds of plasmas we try to produce and has set goals for us. And throughout the years, there have been many, many system studies of fusion systems in the future that, as best can be done, assesses the cost. And the cost of electricity comes out to be competitive. There's a big however. Those studies assume certain success in physics and technology. So assuming that the physics and the technology research missions are accomplished, then they calculate that the costs are competitive. So I think what Dr. Mason says has been backed up by studies. And another caveat is, of course, when you try to project the cost of anything several decades into the future, it's fairly theoretical. Thank you.
Others want to comment about that, about equivalency between the sort of, or are we in the ballpark of a fission kind of investment when we go to fusion if we make electricity that way?
I'll just back up what Dr. Prager said. There have been a lot of studies, and the answer is generally yes. These are large power plants. These are multi-gigawatt power plants typically to get the most efficiency out. And so you're in that ballpark in terms of the scale of the plant. Of course, the issues are different. Fission and fusion are quite different, so the radioactive materials and the things you have to worry about are quite different, but the magnitude of the plant is about the same.
Yeah, make sure I understand that. What is the difference in terms of that radioactivity in that?
Well, fusion works with just deuterium and tritium. Tritium is just a gaseous fuel. There's not a lot on the plant. And the radioactive waste you produce in fusion is mainly the structure that holds the plasma. There's no long-term, highly radioactive waste that you get in a fission plant. Now, the fission people have ways to, if we ever get there, to transmute those wastes in that. But at the moment, you look at very long-term, hundreds of thousands of years kind of waste. Fusion doesn't have that. It has essentially short-lived hundreds of years. You can imagine in a generation or two where that will decay away. And so it's a different radioactive profile. And that's one of the big advantages of fusion.
And what are the other advantages? Why should the United States pursue fusion? There's one.
I'll throw in a few, and I'm sure everybody else has their favorite. Well, there's one. The other, of course, is ready availability of fuel. It's right out of seawater. All you need is deuterium and lithium. Lithium breeds the tritium. There's no danger of catastrophic failure of a fusion plant. The plasma state is essentially quite fragile. If anything happens, you get a leak in the chamber or something like that, the system just extinguishes itself. So it's quite safe, passively safe, if you will. The other thing, of course, it can be anywhere. It's a baseload energy source. I think to back up what Dr. Mason said, if you look into the future, not myself, but energy experts, you only see 2 or 3 baseload possibilities in the future, and it's fusion, fission, if you want to be carbon-free, of course, and possibly solar with storage, but that's a very hard proposition.
Anybody else add a reason to pursue fusion?
I concur with my colleagues on both issues. In relation to your question, yes, fusion is clean, and the fuel is basically unlimited. In the case of deuterium-tritium fuel, is only limited by the supply of lithium. Of course, deuterium is abundant in seawater, and it's unlimited. On the issue of cost, there have been several studies, both about magnetic fusion energy, power plants, and inertial fusion energy. There have been more studies on magnetic side than the inertial side. The United States had a program until last year, the High Average Power Lasers program, that were developing the technology of an inertial fusion energy-based power plant. And so they were doing technology development, the cost estimates of the sort. To the best of my knowledge, the cost is competitive with a fission-based nuclear power.
I would offer as an attribute of fusion that I think we in the U.S. should find attractive the comment that I made about, in one, we talked about the fuel, but another way to look at what the fuel is for fusion is that it's intellectual property and high-end manufacturing. The fuel is not something that you import from the Middle East. It's not something that you run out of, and it's actually the essence of what our economy is built around, which is smart people and competitive industry. And so not only as a domestic supply of energy, but as a possibly significant export market, if we can position our industry to lead in this field, there would be, I think, economic value for the U.S.
Just getting into maybe a softer reason, since the fuel comes from the ocean's water, and that should be accessible to all nations, then you might speculate that the conflict over natural resources for energy would be between nations would be decreased with fusion driving the energy sector. So that's another reason. I mean, it's interesting when most of us entered the field, what drew us in terms of the application was that we were running out of energy. In the 70s, we were running out of energy. There were gas lines, energy crisis. And now, perhaps, really what drives it, the dominant reason probably is no contribution to global climate change. So fusion somehow is almost the ideal, and the dominating reason maybe just changes with the times as the problems that we confront become more clear.
That's great. Thank you. Thank you, Mr. Chairman.
Well,
Thank you, Mr. Chairman. Unfortunately, all the good questions have been asked already. But let me add one other item to your list, Dr. Prager. That's national security. We are treading very tenderly in some treacherous waters with our current energy policies. And I really suspect that far too many people who should know that don't know it. And I'm not just talking about gas lines. I'm talking about the whip that other nations can hold over our nation just because we do not have the energy resources that we would like to have. And it continues to concern me. Endless conversations I get into both inside and outside the Congress. People say, "Oh, well, we have these new sources of natural gas. In Pennsylvania, we can get this new gas. We're all set for years and years and years." Yes, we're set for years, but not years and years. And this inability to deal with reality is just fascinating to me. And people just assume that somehow the scientists, the physicists, the engineers will find a way out of these shortages. And I've taken the opposite point of view. I've often said that natural gas is too valuable to burn. It's an incredibly useful feedstock for the petrochemical industry. I don't know of anyone that's going to be as as easy and cheap to use, and we're burning it. So there's a multitude of issues here, not just energy issues, but resource issues, security issues, et cetera. And I don't think that we as a nation are confronting them as adequately as we should. Having said that, I do wonder, I'm just asking questions about things that I really haven't kept up with the field at all. How are we going to contain the plasmas, and how easy or how difficult is that going to be to actually extract useful energy out of the fusion reactor? And I know it depends on the different types of reactors, but can one or more of you just give me a quick summary of where you see this field going?
That's a great and deep question. I think we have many elements of the solutions to both questions in hand, the much more mature understandings with respect to how are we going to contain the plasma and control it. There's been tremendous progress since actually the late 60s, when there was a transformative event in the invention of the tokamak, which is a kind of magnetic bottle, if you will. It's toroidally shaped. Just a little bit of science here. The plasma, you can imagine, if you can imagine a donut-shaped magnetic field. This is the heart of magnetic fusion, where the plasma, which is charged particles, ions and electrons, they do a very good job of moving along the magnetic field lines, but have a very tough time crossing the magnetic field lines. But there are lots of subsidiary processes that go on in the plasma that can force the plasma, the hot fuel, to make that migration across the magnetic field. What you're trying to do with that magnetic field is confine it for long enough so that you can heat it readily to get up to fusion conditions, where the plasma pressure is such that the fusion between the nuclei takes place. What has happened as the U.S. has really turned towards the science of the plasma, I think, has been a tremendous set of advances in understanding the basic physics for how that plasma is confined in this magnetic bottle, what levers that we can apply to the plasma to optimize that confinement. And I want to make 2 points. One, this is a very deep intellectual exercise, which is, I think, worthy of investment to obtain U.S. capital. These are great scientific challenges, but they're not empty challenges. They're the best kind. They're the ones that are directed towards a purpose, because the answers that we are finding with respect to the science, for example, of optimizing the confinement in this magnetic field, which enables one perhaps to make a fusion reactor smaller, which enables then for the vision of a fusion reactor to be more economically attractive. The science is intimately linked to the final product. And so I think for those that are interested more directly in the final product, it's a compelling enterprise. The U.S. aesthetic, I think, has been extremely strong in terms of understanding that plasma science. As has been emphasized here, though, we think a major frontier resides in crossing that bridge from that magnetic bottle to boiling the water and generating the steam. And that is the material science question and the challenge of harnessing the fusion power. And just as a footnote to all of this, a significant alternate approach that has been mentioned, especially by Dr. Betti, is that of inertial fusion. It's a fundamentally different process where you take a small pellet of fusion fuel. There are no magnetic fields in most versions of the vision, and you compress it very suddenly and rely on the inertia of the fuel itself to contain itself long enough for the fusion to take place. But external to that, the transition to the fusion power and getting the power on the grid looks quite similar. Both of them, again, represent very deep scientific challenges, but again, I think they're the best kind of scientific challenges because they have direct bearing on the output and the attractiveness.
Thank you.
I could maybe add a little bit about the materials, because I think that is a very important aspect, is how you transition from the environment where fusion is happening, whatever form of containment you have, and the environment where you're holding a vacuum and boiling water and so forth. It is a very challenging materials problem that falls into the general category that we like to refer to as materials under extreme conditions. And fusion is perhaps the most extreme of extreme conditions in terms of the temperatures, the radiation damage that the material is subjected to, the presence of hydrogen and the effect that can have on materials. My background is materials science, so while I can't say too much of depth about fusion, in terms of materials, these are difficult problems. And there are different sort of problems than some of the areas that we focus on right now. We at Oak Ridge and around the world are very excited about nanotechnology and the things we can do with that, and thin films for photovoltaics. The materials we're talking about here are different types of steel. It's the materials of heavy industry, and to be honest, it's the development of new steels is not something that, as a nation, we have been doing a lot of in recent times. In fact, you know, many of the materials we have now were developed decades or even in some cases centuries ago. They've served us very well, but they don't necessarily have the characteristics to survive under the conditions that we need, and that's why many of us have talked about the need to look at these materials issues even as we resolve the remaining physics questions of the plasma. And many of those materials issues are the same, whether it's inertial or magnetic confinement. In some cases, they may even be the same or similar to those faced by fast reactors that might be used in closing the fuel cycle. It's maybe not as sexy as nanoscience, but getting better alloys is an important part of this equation.
Thank you very much. We'll have to move on.
I know Dr. Fonck and others want to add, but I want to recognize Dr. Bartlett for his line question.
Thank you very much. Whether or not we're successful in getting fusion power, and I'm skeptical, I'm still enormously supportive of this work because I think that we may find a lot of very other interesting things as we pursue these leading edge scientific inquiries. Dr. Mason, you mentioned efficiency as a major interest. I would like to suggest that before efficiency, we can get huge gains from conservation. Conservation is two people getting in a car instead of one. Efficiency is getting in a Prius instead of a SUV. And we have enormous opportunities for gains in conservation, which can be immediate and free, really, really simple. You know, we have a huge reactor in the sun, and I know that we disparage the use of solar and wind as base load, but I think that would be less technically challenging to make that base load than it would be to produce fusion power. Wherever you have a topography difference, doesn't pump storage work very well for storing the excess energy you have when the wind is blowing and the sun is shining? And I suspect that creating huge banks of capacitors or enormous flywheels would be technically easier to do than trying to do what we're doing with fusion. By the way, I'm a huge supporter. I would, if the capability were out there to absorb 2 and 3 times the amount of money that we appropriate for that, I'd be happy to recommend that to the appropriators. But aren't there enormous opportunities for making solar and wind base load?
Energy storage has huge leverage. If we could store even a small fraction of the grid for 24 hours, it would have tremendous.
You can store it all in pump storage, sir. Just pump it up to the mountain and a lake up there, and then run it down when the sun is not shining, wind is not blowing through a turbine. It's really simple.
And in fact, in Tennessee, TVA has something called Raccoon Mountain where they do exactly that. So it does work, but if you look at the capacity and the efficiency of it, it's hard to see it scaling to the level that we would need. Now, if you push renewables, as we should, you can probably get up to about 20% and still handle the intermittency. And you could push that farther if you had better energy storage, whether it's electrical energy storage in the form of batteries or the compressed air. So I think there is tremendous leverage in storage. It's an area we should and are investigating. But on grid scales, I believe it is a very challenging problem. And it's one that is maybe not quite as difficult as fusion, but it's in the same league.
Dr. Betti, you mentioned something else that I think most people don't understand. You said that we should be electrifying our transportation. And, you know, we use two kinds of energy. One is electrical energy, and I think the future for electrical energy is okay. With nuclear, whether it's fission or fusion, with wind, with solar, with micro hydro, for which there's considerable potential, and for true geothermal, where we're tapping into the molten core of the Earth, I think that we can make about as much electricity as we ought to be using. That's not true for liquid fuels, because there's just no combination of substitutes out there for liquid fuels. And when gas and oil and coal are gone, and they will be, we're going to be living on electrical energy. And so I think that too few appreciate the concern that you have that we need to be electrifying transportation, because that is one essential use of liquid fuels. Some other use of liquid fuels we can use electricity for, but for that one now, it's tough. We just tore up all our streetcars. We were proud that we were doing away with these antique things, and we tore them all up. Now we need to be putting them back. Thank you for your recognition that we need to be doing that. Welcome a second line of questioning, Mr. Chairman. I yield back.
Thank you, Dr. Bartlett. It looks like we are all going to probably not be able to do the second line and, with the votes being called. So I'll recognize Mr. Rohrbacher. And,
Dr. Rohrbacher, that was quite a...
It's a frightening thought.
Let me just note, Mr. Chairman, that we heard that before, back in the 1970s, we saw the gas lines, and we were told that there was an imminent situation where there'd be this massive shortage of energy, and that was proven false. And now we're using an excuse of greenhouse gases, which will cause global warming, as an excuse to move forward on certain things. And quite frankly, none of the predictions of those people who have been advocating global warming have come true. In the last 9 years, there's been cooling. And in fact, there are now reports that the polar ice cap, the one polar, the other, the Antarctic was never contracting, but the polar ice caps are now expanding. And so this idea of greenhouse gases causing global warming is the basis of a lot of things, but I would not use it, if I was in the scientific community, as an excuse for moving forward with fusion energy research, because that, I think, is becoming something that, again, is another theory that will be proven false, and that is being proven false by the way the world is acting. When I was a young child, when I was actually in, I think, 5th or 6th grade, I saw a wonderful movie about fusion energy. And remember Mr. Science? I don't know if you remember those things. So it was wonderful. And fusion energy was the energy of the future. And you know what? I'm 62 years old now. And I take it from what you have told us today that we haven't even had ignition yet after all of these years of research. And my calculation is that we've had $40 billion worth of research, and we don't have ignition yet. Dr. Bartlett's observations is that research money, there is limited research money in this country, might well be put to better use in finding about how we can utilize the heat from the core of the Earth or the pumping technologies.
I want to do both.
Both, and I do too. But we have limited research dollars. Why is it that fusion, after all of these years and all of this money, and with so little actual progress, meaning we haven't even had ignition yet, even for a second, I believe, why should we continue? Why shouldn't we transfer this money to some of these other technologies that perhaps would be cheaper? And one last thought, Mr. Chairman, and that is, and I'd like the panel to go to that question, and that is, I do believe that we should have at least one skeptic on the panel for every subject that we look at. And it's okay. I mean, all of you gentlemen have incredible credentials, a lot more than I do, that's for sure. But some of the issues that I'm raising should be raised by people who've got PhDs in this and be able to have a dialogue so that we'll have something to decide here in the panel rather than just accepting one point of view. But I've made a couple points. Please feel free. I know you've got some things to counter there. ahead.
Well, if I may, I think there are probably many facets that people might comment on. I think actually I have a view that the urgent things and the opportunities we have is, in fact, to address the questions of credibility that you raise. Our science basis is such that I believe we have good confidence in what is required of our next step to get to the stage of what we call burning plasmas in magnetic fusion. I think that is what you're referring to when you're talking about ignition, where we're getting more energy out than we're putting in to heat it and control it. I think our understanding, the scientific basis for getting there is quite strong. So it is, and we understand it, I'm going to oversimplify it a little bit by saying it is a question of scale. We understand that the present devices that we have invested in, are not appropriately scaled and don't have the control technologies that we need to reach the scientific regime that you're talking about. Having said that, in the early part of I think it was in 2001, there was a technical assessment of several options in magnetic fusion that we would pursue to understanding this burning plasma state. Just also with respect to credibility, I think if you burrow down one more level, you get to the question that people have been raising here, and that is the question of materials and harnessing these fusion plasmas. I would be delighted. I would view it as a major accomplishment collectively in our careers to be able to point quite definitively to the answers to your questions demonstrably. I believe the scientific understanding is strong that we have a confident and strong bridge to the demonstrations that you're talking about. Understand also that publicly there are many who desire exactly the sort of thing that you're talking about. I think we're within reach of doing that.
Well, I've supported nanotechnology and these things, and I do support them, but they take research money, and we've had $40 billion eaten up for fusion that perhaps had we put into nanotechnology or some of the other more, that we have some actually demonstrations of progress, perhaps some of the other issues you're dealing with would have been solved.
Remind my colleagues, we now have about 8.5 minutes left to vote. And what I'd like to do is I think rather than asking these gentlemen to wait 40-plus minutes while we go vote and come back and sometimes don't come back, I'd like to do is close. But Dr. Bartlett had some questions earlier that I know folks wanted to respond to. I'd invite if the witnesses, if you have additional questions or responses. I know there were some eyebrows raised about whether $40 billion is the correct number that has been spent. Please feel free to give us some written comment. I'd just like to close with two questions. I want to make sure we get one issue on the record real quickly. My understanding is that the inertial fusion energy effort is, I'm not sure the proper way to say it, but does not necessarily have an official home within either NNSA or the Office of Science Research. And I'm wondering if that's something we ought to consider addressing. I'll give you a couple minutes, but we're down to about 7 minutes to get over to the vote. So any brief comments? Dr. Betti, you're in charge of that operation.
Yes. So first I should just really briefly mention the fact that the physics principles of inertial fusion energy, what we call ignition, has actually already been demonstrated because that's how hydrogen bombs work. Okay. The problem is that to trigger ignition in a hydrogen bombs, we use an atomic bomb. We use an atomic bomb. But this is important. We use an atomic bomb. So what we are trying to do is to replace the atomic bombs with a driver, a laser. Okay. But the physics principles have been demonstrated. What hasn't been demonstrated is that we can reproduce this in a laboratory. Okay. So that's an important distinction. In terms of the inertial fusion not having a home, inertial fusion energy doesn't have a home. Inertial fusion does have a home in NNSA for weapons applications.
Good point.
Okay, so it is very important, I think, and very cost-effective to use the facilities that have already been built by the National Nuclear Security Administrations for billions of dollars that are already there, including the National Ignition Facility, Omega Laser, and so on, we can use this to study the energy applications of inertial fusion. And so that's why I think it's critical to have a home for fusion energy, inertial fusion energy, and use these facilities. We don't need a lot more facilities.
So you've got,
you've
got the physical home in terms of the infrastructure.
And the infrastructure.
Bureaucratically, where should the home be? NNSA or DOE? Or both?
Well, I mean, this is really not really for me to answer the question. I mean, I would think that the fusion energy development program should be within the Office of Fusion Energy Sciences, but that's my personal preference.
Let me ask one last question, and my colleagues are ready to go. Quick question. If anybody were to say, hey, we don't need to conserve, I want to really put the punctuation point on Dr. Bartlett's. If someone were to suggest we don't need to engage in conservation or renewable energy development because we've got fusion right around the corner, anybody agree with that at all?
I think this is not an either nor. We absolutely have to conserve and do energy efficiency, but we should not fool ourselves to think that that by itself will get us.
I get that, but it would be foolish to say that fusion's right around the corner, it's going to solve all our energy needs. Mr. Davis is here. I'm going to actually, very quick question. My colleagues are free to head out, but if you have other questions to ask, we will not be returning for this panel.
It's a common question, and Dr. Mason, I'll probably converse with you later today about the question I'm going to ask. There's a great deal of excitement about wind and solar and other renewables being discussed now. If, in fact, as some believe, that will supply our energy needs, why do we bother with fusion at all?
I think that the challenge is that in order to get to the sort of goals that I think we as a nation have in terms of energy independence and emissions, we are going to need renewables, we're going to need storage, we're going to need base load, carbon-free generating capacity as well. And so we should certainly be using renewables as much and as quickly as we can, but they will not scale to meet all of our needs. And that is where a clean base load generating capacity like fusion has the potential to be is very valuable as part of our longer term R&D portfolio. Not to say that we shouldn't be pushing as hard as we can, as fast as we can on the things that we can do easily and quickly, like energy efficiency.
We get roughly 20% from fission nuclear energy today. What would you see as a possible projection from fusion, nuclear fusion, and the research we're doing?
Fusion can play exactly the sort of role in our electric grid that fission plays today, and in fact, in the end, fission has a fuel supply need. So in the very long term, fission would be probably superseded by fusion.
Dr. Ehlers had a final comment.
I want to thank you for holding the hearing. It's been very, very useful to me. But I also want to congratulate you and the panel. I think this is the first hearing we've had on fusion that didn't result in questions about cold fusion. So we did have a little bit of disagreement about climate change, but maybe we're making progress here. Thank you very much. Very useful.
I want to echo Dr. Ehlers' comments. The frankness and honesty about both the potential and the limitations and the challenges have been very refreshing and much appreciated by myself and I think by my colleagues as well. Again, thank the witnesses for their time and for their many years of service, and we look forward to continuing the dialogue. If you have additional comments, the record will remain open for 2 weeks to offer those, and with that, the hearing stands adjourned. Thank you very much.